Okay, this is 6.5, exponential and log applications. And most of these applications are set up in exponential format. They're going to be set up in the exponential format, which was chapter 5. And then what you're going to do is you're going to use logs when appropriate in order to solve that exponential function. Okay, so our basic exponential format was something that looked like this. Y equals A times B to the power of x minus h plus k. When it comes to an interest rate type story problem, a dollar sign value, a money value model, P is your principal amount. That's your initial amount, how much you start with. Remember, we talked about A right here being something called the initial value. And so A was called the initial value. That's the amount that you start with. So think about a story problem, the amount that you start with. If it's money, it's how much money you're initially investing. If it's a population, it's the initial population. If it's a piece of radioactive material, it's how much you're starting with at the beginning. Okay? B is your rate. It's how fast the money, the population, the radioactive material is either growing or decaying. And when it comes to financial stuff, if you follow the red ink here, if you have something called growth, 75% growth, that means that your rate is 1 plus 0.75 or 1.75. That means you have 75% growth. If you have 75% of the original amount, 0.75. But we had a third way of representing this idea. And the third way was decay. So if we had 75% decay, we said that was 1 minus 0.75, which is 0.25. So 75% decay means 25% of the original amount. So you have to be very aware of the words and what they're saying, what the words mathematically mean. If they say this thing has 75% growth, that means your base is 1.75. If they say this thing is 75% of the original amount, then that's not 1.75. It's 0.75, which is the same as 25% decay, right? 75% of the original amount is the same as 25% decay. And then, of course, if they say decay, then you subtract it from 1. These two words, growth and of original amount, these two statements are very different statements. They kind of look the same. Oh, it's 75%, 75%, 75%. No. 75% growth is very different than 75% of the original amount, which is 25% decay. The tricky part, actually, is going to be the pink highlighted area, which is the exponent, which is represented by time. And when you're doing these models, you have to make sure that time is consistent. And what I mean by consistent is the units of time. Sometimes they'll give you one piece of information that is in minutes, but then they ask a question that is in hours. And you have to do a quick little unit conversion to get minutes to hours to make sure that things line up correctly. And we're going to look at that. So make sure that the units of your time are consistent. So let's look at the two basic models that you're going to see. So the first type of problem that you're going to see is a doubling problem. And when you have a doubling problem, the function is a of t is equal to a times 2 to the t divided by d. This is the base model for an exponential that's doubling. This base of 2 means you're doubling. And this d right here is the doubling time, the amount of time it takes for the population to double. This t up here is the time being evaluated, which relates to this time right there. The other type of problem that you're going to see is a halving problem. The model is kind of the same. It's a of t equals an initial amount, which is a, but instead of a base being 2, it's going to be 1/2. And you have the same T over D, except for this time, the D is not the doubling time, it's the halving time. The amount of time it takes for something to be cut in half. The most popular example of this is radioactive decay. And with radioactive decay, you have something called a half-life, which is the amount of time it takes for half of the mass to become not radioactive. So you have bacteria, and it divides into 2 cells every 40 minutes. The initial population is 6 bacteria. So at time 0, how many bacteria do we have? How many do we start with? 6, right? At time equals 40 minutes, how many bacteria do we have? 12, because remember, they double. After 80 minutes, 24. So we're going to say the population at time t equals the initial amount times 2 to the t divided by d power. And we got to fill in some stuff. So p of t equals, what is our initial amount? I think that was 6. So we'll put a 6 in here, times 2. And where does the 2 come from? The 2 comes from the nature of the problem. It's a doubling problem. So our base is 2. Every generation we double. And now the tricky part, t divided by d. And notice the very first question says, find the size of the population after t hours. Not t minutes, but t hours. So after 1 hour, what is the population? So at 0 hours, we still had a population of 6. After 1 hour, you know it's going to be in between these 2, right? 1 hour is in between 40 minutes and 80 minutes. So we know it should be a population in between 40 and 80. So your guess is 18. Okay, I'm going to write down 18 with a question mark, because that's kind of your guess. What is the doubling time? And again, because we want to know this in hours, we need to come up with the doubling time in hours. So how many hours is 40 minutes? 40 minutes is 40 sixtieths of an hour, which becomes 4 over 6, which becomes 2/3. So that's what we got to put in for D. So this is going to become t divided by 2/3. I really don't like t divided by 2/3, so I'm going to invert and multiply. So it's going to be 3t divided by 2. So our final equation is going to be 6 times 2 to the 3t divided by 2 power. And now you can take any time in hours and plug it in there. Let's see if it works. What's p of 1? 6 times 2 to the 3/2 power. So what's the population after 1 hour? Is it 18 like we guessed? No, it's actually a little bit less than 18. Because remember, this is not a line. The graph is a curve. This is the answer to part 1. So here's part 1. Here's the answer to part 1. And now we're going to do 2 things with this equation. One thing that we're going to do is we're going to give you a time and have you plug it in and solve it and get a population. That's the easy part. The hard part is we're going to give you a population and ask you to solve for the time. That's going to involve a logarithm. For part B, t equals 5. So we're going to take our equation and find p of 5, which is 6 times 2 to the 3 times 5 divided by 2 power, or 1086. So this is 1086 bacteria. When will the population reach 30? What's your guess? The next doubling is going to occur after 120 minutes, and that will give you 48 bacteria. So when is the population going to reach 30? I don't know, somewhere in here, right? In between 120 minutes and 80 minutes. We know that our guess is going to be probably somewhere between 85 and 95. Is that okay? Let's just put that down for a guess. And if we get a number, we do a calculation and we get a number like 5, we've done something wrong. If we get a number like 158, we've done something wrong. But if we get a number like maybe 96, we probably did it right. So how are we going to do this one? Well, we want to know, when will the population reach 30? So for part C, let's go back to our function, and we know that we want this population to equal 30. So the equation becomes 30 equals 6 times 2 to the 3t over 2 power. Solve that equation for t. Divide by 6, divide by 6. Multiply both sides by 2. Zip. Divide both sides by 3. Zip. And there's your answer. So if we run change of base, we should get 2/3 times log of 5 divided by log of 2. Or you could say 2/3 ln of 5 over ln of 2. Your choice. So let's try this and see if we get a number about between 85 and 95. 1.54. What? This is 1.54 hours. Remember the time change. When we did our estimate, it was in minutes, right? How do we convert hours to minutes? Is that about our estimate? We said between 85 and 95. So it's about 92.9 minutes. So going back up to the question, when will the population reach 30? My guess is they want you to put that in terms of hours. So you need to put in the hour number that we had, which was the 1.54. Palladium 100 has a half-life of 4 days. Conceptually understand this, and then I'm going to erase these numbers. So at time equals 0, let's say you have 100 grams of radioactive material. This has a half-life of 4 days. So after day 4, how much is left? 50 grams. After day 8, how much is left? 25 grams. After day 12, how much is left? After day 16, after day 20. Every 4 days, the population gets cut in half. So we're going to say the amount of radioactivity over time is equal to the initial amount, which is A, times 1/2 T divided by D, where D is the number of days of the half-life. So our function is going to be A times 1/2 to the T over 4 power. And now they give us a little piece of information. They say after 16 days, the sample of palladium has been reduced to a mass of 7 milligrams. So that means at day 16, you have 7 milligrams. What was the initial mass? We could brute force this. We could count backwards, right? You could say, well, at 12, you had 14. At 8, you had 28. At 4, you had 56. And at time 0, you had 112. But let's pretend we don't know how to do that. Let's pretend that we didn't have a nice number. So how do we solve this? You know you have 7 milligrams equal to an initial amount. We don't know what that is. We think it's 112, but let's pretend we don't know. Times 1/2 to the 16 divided by 4 power. So that is A times 1/2 to the 4th power. 1/16. And now how do we solve this? So we'll multiply this by 16, and we'll multiply this by 16. Over 1, blah, 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 blah. Those cancel, and you get A equals 7 times 16. I don't know, what's 7 times 16? 2, carry your 4, 7, 8, 9, 10, 11. Look at that, 112, which is the same answer we got when we brute forced it. So it must be right, and it is. So now we know our initial amount. We know that we started out with 112 grams of palladium. What is the mass after 8 weeks? So now our formula is the amount per time is equal to 112, our initial amount, times 1/2 to the T divided by 4 power. So we're going to take this initial amount that we just solved for in part A and leverage it to solve for part B. The question is, what is time? What goes in for time? And remember that our exponent is based on days. We would like to know 8 weeks. So that's A of what? 8 times 7, which is 56, right? How many days are in 8 weeks? 56. So that's going to be 112 times 1/2 to the 56 divided by 4 power. 14. So this is 6835 with a couple zeros. And what is this in units of? Milligrams, right? So that'd be your answer. 0.006835 mgs, milligrams.